So thank you, Sebastian. Hello, everyone. So this is a work that I did with Pierre Escamilla and Jeongran Lee. We are all from Nokia Bell Labs in the team of Matthew Andrews. And so the goal will be to infer trajectories of objects using various camera feeds. So the background, so this is a project that is related to digital twins, metaverse, and augmented reality. So maybe you know that Nokia is partners of this arena, and so we have the possibility to get camera feeds. And this is where you have hockey competition that are played in Finland. And so the idea would be if we have all the camera feeds, could we enable a kind of augmented reality, allowing the viewers to move from one camera to another, like on the left screen? So here you can see that during the transition, no players appear. Or even better, could you do what we call spatial clustering? So I don't know if the video will work, maybe not. But you could look at this on YouTube. And so the idea is you can move around the table and see the player evolving on your table. Okay. So now the question is, how do we do this? So the first part will be related to computer vision. So first of all, what we get is the raw image on the left. So as you can see, this is distorted, rotated, flipped, etc. So we have some processing to run to get clean video. And so to do this, we will require what we call the camera matrix in computer vision that I will denote by K, and the distortion vector that I denote by D. Once the video is undistorted, we can use a neural network. So for example, YOLO-V8, which is able to recognize humans given a camera feed. And so the main advantage of YOLO-V8 compared to the previous version resides in its ability to provide the detection masks. So here you can see that the detected humans are painted in blue. This is because YOLO-V8 returns the detection masks. And so once we have the mask, we are happy because this will give us the possibility later to build 3D models given the perception of a given player from various cameras. So now the question is, how do we locate the player in the space? And so to do this, we will approximate detection by using the pixel in the middle of the lower border of the bounding box of the detection. So this yellow star. And then using the camera matrix, we will be able to map every pixel that lies on the ground to a 3D coordinate. So to do this, there are some maths to do. So we will require some information that lies in the camera matrix. So for example, the focal distance, the principal point, etc., etc. So I will go fast because the presentation is short. But intuitively, the idea is if you assume that you want to map a pixel UV with X, Y, Z coordinate, then you can use those equations if you assume that the pixel lies on the ground. So you assume that the ground is flat, which is the case of a hockey rink. So those equations allow to find the mapping. So from this, we are able to map each pixel with a 3D point, but in the camera frame, and we want to remap those coordinates in the world coordinates. So to do this, we will rely on a rotation and a translation matrix and use quaternons. So this is common stuff in computer vision. And so we will be able to remap 3D camera coordinates to 3D world coordinates. So to sum up this first part, we start from the raw image. We undistort the image. We use YOLO-V8 to find the detection mask. We get the corresponding pixel. We use the flat ground assumption, and then we are able to map each detection with a 3D coordinate in the world. So now the problem is we have several cameras. And so unfortunately, due to the uncertainties, the coordinates provided by the cameras are not exactly the same. And so we would like to detect, so for example, assume that you have 3 players and each shape corresponds to a camera. we would like to rediscover that those detections correspond to the same player, and those detections correspond to the same player, and those detections correspond to the same player. So it looks like a clustering problem. It recalls k-means, but it's not k-means because we don't know k by advance. Maybe we see all the players, maybe not, so we don't know k by advance. And so that's why we will have to reformulate a k-means formulation to fit our needs. So I will skip this. So here, this is just to explain what I said. We don't capture the whole ring, so we might miss some players. And as our YOLO-V8 is inaccurate, we might miss some players. And so we don't know K by advance. So to do this, we will use an ILP. So V is the set of detection. C is the set of camera. And my function C maps the detection with the camera that has captured the detection. And then I have a distance, typically the Euclidean distance, that computes the distance between two detections. And so the first thing to do is to formulate what is our objective. So this is the equation that is below. Without entering too much in the maths, intuitively the green part encodes the intra-cluster distance, while the red part encodes the inter-cluster distance. And so ZUV means that U and V, those two detections belong to the same cluster. So depending on whether ZUV equals to 0 or 1, it will contribute either to the intra-cluster or either to the inter-cluster distance. Once we have solved our problem, so we start with this and we will get this because we are able to assign each pair. So for example, if this guy is I and this guy is J, so this Zij will be equal to 1. But it's not enough, of course, because here we have only the objective. We have to define some constraints. So first of all, we don't want to gather detections that are too far away each other. So that's why we define some radius constraints. Then we know that our detector detects at most once each player. So this bound, this provides us an additional constraint. And finally, also two detections U and V captured by the same camera cannot belong to the same cluster, which once again induce a new constraint. So actually, it imposes the value of some variables to 0. Now it's not enough because this is a clustering problem. So if I and J and K belong to the same cluster, then so I and K must belong to the same cluster. So you have some implications that are written here, but this is not yet linear constraints. Fortunately, we can linearize them quite easily. And once we have this, we are quite happy because this means that our problem is an ILP, and so we can directly use a solver. So let's go. We have solved the problem of the spatial clustering. So at this step, for a given frame, we are able to unify the perception of each camera. Now the question is, what if I want to rebuild the trajectory of each player? So assume that you have a single camera or a unified camera. Now I want to rebuild the trajectory. And so to do so, I will have to solve another optimization problem that I call the temporal clustering. And so the idea is assume that you have a set of consecutive detection. Maybe sometimes you have some hole in the detections. It might happen. So the grayscale corresponds to the freshness of the detection. We would like to pair consecutive and close detection to map them to the same trajectory. So for example, the blue trajectory, the pink trajectory, and the green trajectory. And so this is a quite common problem in optimization and in computer vision. This is very close to what we call the Hungarian algorithm or the Munch-Kress algorithm. The main difference here is sometimes as our camera might miss a given player, we want somehow to bufferize detection that might have temporarily vanished. And so this forces us to slightly reshape our problem. So what is the Hungarian algorithm? So shortly, assume that the pink part corresponds to the detection at t, and the blue part corresponds to the detection at t+1. We want to find an assignment represented by the red arcs that is that has a minimal weight and that pairs the pink detection with the blue detection. And so the formulation is quite easy because this is more or less just minimize the distance between the pink part and the blue part, knowing that you have some flow constraints. So for each vertex, either in the pink part or in the blue part, you have at most one red arc. Actually, you have exactly one red arc from the blue part because the blue part is smaller than the pink part, and only the inequality for the pink part. So here, this is the flow constraint correspond to this set of constraints in this particular instance. Okay. So once we have this, so as I said, we can say bufferize some detection that seems to have vanished. It's a slight adaptation, not very complicated to implement, but it allows us to make our algorithm more robust. So now if I combine the spatial clustering frame by frame, and then I run the temporal clustering to rebuild the trajectory, I can rebuild this kind of things. So hopefully it will work. Yes. So here you have so each rectangles here correspond to the perception of a given camera. Here, this is what we get when we unify everything. And so as we can see, we can rebuild some trajectories. So it works quite well. Okay. So to conclude, I have presented an algorithm that allows you, given some agent's position, to rebuild, provided by several cameras, to rebuild the trajectory. So to do so, we rely on a spatial clustering that unifies the perception of each camera. This is achieved using an ILP formulation. And then we rebuild the trajectory of those unified detection using a temporal clustering algorithm, which is based on the Hungarian algorithm. And that's all.
Thank you for this nice presentation. So I would like to know if your algorithm is centralized or decentralized.
Centralized.
Centralized. And there is any way to decentralize it in a architecture where you assume that the cameras may communicate with each other? As you may know, there are some works on how camera do.
So possibly, yes. You might imagine indeed. So maybe this is not the right use case because here you are in the same infrastructure. So it's the decentralized use case is not so important. But maybe I guess that in the decentralized case, you would have some area that are overlapped, and then several entities monitoring each of those areas. And at some point, you want to merge detection that are in overlapping area. This is the only use case that I see where a decentralized version of this algorithm could be useful. So is it what you have in mind, for example?
No. So for instance, when you are doing tracking, whatever kind of tracking, so having a communicating camera is more efficient than a centralized approach.
I don't see how you would do this, but it would be another algorithm. So
totally different.
Yeah, it's totally different. So I don't know how to do so. Maybe it's possible, maybe not. Here, the assumption is we trust every camera and they are close enough, so we don't require this.
Collect everything on a central site.
Yes, exactly.
Okay, thank you.
Yeah.